Hi everyone. In this tutorial, we're going to look into minimal surface construction and basically trying to do this using Grasshopper tools. And this will be kind of a mathematical investigation into form finding approaches, as well as understanding topology and developing surfaces that are continuous in nature. Let's go over first what a minimal surface is. It's basically a surface that locally minimizes its area. So think about a soap film and how it basically achieves zero mean curvature when it's basically forming in between kind of a boundary area, right? So this is kind of a naturally occurring phenomenon, but it's also explored in the area of mathematics because it's basically giving us very interesting surface properties, mathematical topologies that could be used for different types of design applications because it can fill volumes, it can generate surfaces that are continuous, but it's also producing actually developable surfaces. So for this session, we're going to look into the construction of gyroid surfaces, and gyroids are basically triply periodic minimal surfaces. Now, what that means is it basically periodically repeats in a space, right? So triply periodic means it has three ways of symmetry in the way it can be deployed inside of a volume. And they're discovered by Alan Schoen in 1970, and they basically there's actually a Wikipedia page that you can show. You can actually explore the 3D form here, and you can see there are like these pockets as well, and the surface actually repeats. It's actually a modular surface that could be constructed out of a subgroup of surfaces. So we're going to look into this construction, but I'm also going to include some links in the description for those of you that are interested in looking at other types of minimal surfaces, because there are so many that are still being discovered, and these all have different mathematical properties. So if you go here to triply symmetrical surfaces, the gyroid, you can find more information about it here. There's a famous Schwarz P surface. It's kind of built out of this module that could be repeated in space. So there are a few other examples that you can look into, but it's kind of a nice exercise to study topology, surface construction, and how to build this parametrically as well. So for this exercise, we're going to look at the gyroid, and the gyroid module actually looks something like this, but it's actually built out of this kind of quadrant that we're going to look into. So we're going to build this first as like a polygonal mesh, and then we will try to subdivide it recursively to smooth the geometry, right? So we're not going to build this out of curvilinear surfaces, but we're going to build it out of planar pieces, actually, which will make the topological investigation a little bit more interesting. So if you look closely at this module, you can see that we have these arches. So I'm going to abstract these as polygonal lines. So there will be a peaking point here, and there will be a polygonal line. But if you look, if you inspect this form a bit, you can see that the construction of the module, the arches actually are rotating on each face. So the first arch is here, the second arch is on the face on the side, this arch is on the top face, right? So they kind of alternate and they kind of rotate about this cube. So we will first develop this in an analog way to understand how the surface topology could be constructed, and then we will look into the parametric construction of it in Grasshopper. So I already have the template here, but I'm going to first walk you through the construction. So let's create a new document. So this is actually the gyroid as like a module. You can see these arches are kind of alternating, right? So this is kind of top view, this is in the plan, this is on the side. But to see it a bit better, I'm going to just draw, let me see, let's snap to the vertex and extract the wireframe and delete this so you can see a bit better. I'm also going to flip this around. So you can see that this arch is on the bottom plane. This arch is on this face. So we actually get one arch on each plane, and they kind of alternate in this fashion. And we will first try to build this parametrically, basically see if we can use this construction to build kind of a larger assembly, something that looks like this, right? So I'm going to walk you through how to construct this out of meshes and how to parameterize it later on. Okay, so let's get going. I'm going to start with a box. So let's start with a center box. And we're going to first try to reparameterize this using polygonal edges. So I first need to find this bottom face. So to find it, I basically deconstruct the brep. So now we have list item. So let's get 0 to 5. This would be one of the faces. So this face has this arch coming this way. I want to find the bottom face. So let's see, it's actually right here. And then I'm going to do another deconstruction. And I want to find this edge now, right? So let's find that edge, list item again. 0 to, I said 4, but actually 3. So we find this edge. And I want to evaluate points. So let's do evaluate curve, reparameterize, and do a midpoint evaluation. So from this point, there are a few options. So we can either move this point towards the center of the this face. Actually, that's actually not bad. So we get the center of the face, but let's actually do it here, center of the face, and then let's draw a new line here. So from this to this. And I want to do another evaluation here. So this could actually be points on curve. Maybe we want to keep it as is, but maybe we want to also parameterize this point evaluation at some point. That's totally up to you. So let's find this midpoint. There we go. So we found this midpoint, and we have the edges here. So the edge, let's grab its endpoints. And what I want to do is connect these as a polyline. So we can do something like this, or you can actually draw lines. Either one would work. So we go from this to that, and from this to that. So we get these two new line segments. Now, why am I drawing it like this? It's basically, we want to construct this as a mesh geometry. So for the mesh, this doesn't actually need all of points. We can just work with triangles or quads. So essentially, this is, as you can see, it has more faces because it's recursively segmented. But initially, we just want it to be defined as these quads. So we just need actually 4 points to define this as mesh faces. And then once you join these, you'll be able to subdivide it so it becomes smoother in geometry, actually. So it's kind of a way of handling topology. So now that we have done this, let's actually move to this side. And for doing that, I'm just going to move this curve around. We can actually keep some of these parameters. I'm just going to move these out a bit. So they will be shared. I'm just going to keep this as a group. And we just want to copy this group. And this is kind of a trick you can do. So I'm going to move to this face here. So let's find the index of that face. So the index is actually 0. And I want to find this edge this time, right? So I can go from the edges. So that's the edge. And I want to keep adding these to my curve lists. So you can see that I'm actually building these arch sections using polylines, right? So we built this bottom one, this side one, and the top one is actually facing down. So it's going to be on the side. So let's find that as well. Just going to copy this all the way down. So let's find that face first. This is the face, and it would have to be on this edge from the top, right? So I'm going through the indices, defining the top face, and then we can append this to this list as well. So we keep building our profile around the surface. All right, so we have 3 more to go. So the next one is going to be, let's see, this back edge, and it's going to go down. So let's go from here. Is it actually the back? No, it's actually the top. It's going to go in. Okay, so let's go back. It's going to be this edge, and let's find, yeah, this is it, right? So we are moving down here, but we are moving inward on the top face here. All right, so now we have, let's see, we're going to move to the back face. So this arch, maybe it's a bit difficult to see, but you can see this arch is actually on this face here. So let's go make another copy. Let me add these again. So let's make another copy. And this time I'm going to move to the back face, which is right here, and then the opposite edge here. All right, maybe I should bake this box and zoom to it so that we can see it a bit better. Okay, there we go. All right, so now we have built all of these, and then I'm going to attach this as well. So I have one more edge left, which is the bottom face, and then it's going to go in on this side. All right, so that face is going to be the bottom, and the edge is going to be this edge. Then once I attach this, that's basically the edge construction. Actually, I made it incorrect. So you can see I already done the bottom face. This is supposed to be this face here. So let's find that actually and fix it. So it's going to be this one, and this one is going to be index 0. Perfect. All right, so we have these. Let's actually turn these off, turn this off, and turn this off. Perfect. So this is my polygonal construction for the gyroid module, right? And we also have a volume, which gives me the centroid. So if I were to extrude all these edges in a linear fashion, let's see. So if I do extrude to point, this is basically kind of a preview of the polygonal construction for the meshes, right? But it's since we are doing it on these lines, it's actually triangulating it. So I'm getting 12 untrimmed surfaces, and that's not what we want. What we want is we want to use this centroid, but we want to build quadrants or quads for the mesh construction. So there should be a quad here. So let me show you what I mean by that. So if I bake this and then bake the centroid, I want a mesh face here. So if you go to mesh tools and you click on single mesh face, you can start with the centroid, go here, go to the edge and go down. And that's one face. And we want to keep building these along this dimension. And the reason why we are doing it this way is so that this basically will describe the topology of the surface. But once we smooth it out through subdivision, it will actually maintain the topology, but it will add more faces. So this line would actually become kind of curvilinear, right? So that's essential for the construction of these minimal surfaces. So you can see we have kind of 2 directions for the faces. And if I do it like for some reason, let's say I do it counterclockwise construction, I'm actually getting an irregular direction. I have back faces on for visualization. So if you go right click here, go to display options, and under shading settings, I have a back face setting set to red. So that means my surface normals, where they are facing, I'm getting the surface material, but the back faces are getting this color. So one thing that you need to make sure in topology construction is we want these surfaces to be facing the same way, right? So that's kind of essential for giving it thicknesses or directions later on. So if you have inconsistency here, you should flip surfaces basically. All right, so how can we do this parametric construction? So rather than building these one by one, we can actually build this parametrically. So you can explode this curve. Let's do explode. All right, so now we can actually look at a point list. So this kind of works for the gyroid construction, but maybe for others, you might want to do it in a separate way. Let's see, we got 12 lines. Oh, we didn't join them actually. So let's join these curves first. Okay, we should have 12 lines. So I'm going to go to wireframe mode. So we start from this corner here, 0, 1, 2, 3, 4, going counterclockwise and ending up at index 12, right? So we have basically 12 points to cover. So our construction is going to use the centroid, and we're going to build these quadrants that I just showed you. So we need these triplets. So 2, 3, 4, 4, 5, 6, 6, 7, 8, 8, 9, 10, 10, 11, 12. And we also need 0, 1, 2. So we need to create a series for those indices. So let's look at how we can do that. So I want to generate, we have 6 faces. No, we're going to have 8 faces actually. Right, so we're going to have 1, 2, 3, 4, 5, 6. No, we're going to have 6, sorry. So we're going to have 6 series, and they're going to start from, let's see, we're going to start with 0 and switch to 2 and switch to 4, right? So they're going to increment with the indices of 2, and this will be the new starting point, starting index, and we just need this to be 1. So that should give me, let's see, this will be triplets though. Okay, so that should give me the number sequences that I need. So 0, 1, 2, 2, 3, 4, 4, 5, 6, and 10, 11, 12. So now if I do list item, this is the vertex list, this is my indices, and that should give me all the grouped points. And one thing that I'm missing is the centroid. So the centroid, I'm just going to do list insert items. So I want to insert the centroid here, and I want to insert it to the beginning of these lists. So we always start from the centroid and then go through these points. So it will start from here, go to 2, go to 3, and 4, basically. So that should give me 6 lists with 4 points each. So if you want to double check this, you can do just a quick polyline, and you can see it's actually drawing the border of the quads. But what I want to do is actually construct mesh. So we're going to do this parametrically. So for the construction, for the mesh, we just need to supply a list of vertices and a list of faces. So the faces will be quadrilateral. So I already have 0, 1, 2, 3, but if you don't, you can actually do a mesh quad that already has the indices that we want, so 0, 1, 2, 3. We don't need to supply these indices, although you can if you want to. For instance, I could have supplied the individual indices here and just gave the list of vertices here. That could be one way of doing it. Maybe we can also look into that, but this would be just, this would also work with separate lists, basically. So if you supply this to vertices, you can see this is my mesh geometry constructed parametrically. Now, why are we doing it all this way? Is because we can actually now use this construction parametrically, right? So I can actually change the behavior of the surface as well as the evaluation of these points. So that will give me some sort of parametric control over the gyroid. But essentially this construction is kind of consistent. And just to show you how I got this shape, so the next step is actually pretty straightforward. So if you do mesh join, or we can look into Weaver bird function. You have to download this plugin. But if you go here, do join meshes and weld, so you can just like flatten this list, and you can do Catmull-Clark, for instance, that will give us a smoothed out geometry. So if you bake this mesh, you can see that's kind of a third level. This is the second level, so I'll just plot these steps of segmentation or subdivision. And if I do 1, 0 would be basically the same. If I do 1, that should have just 2 faces. So you can see at each iteration, it basically starts with the same mesh face, but one recursive subdivision means the quad becomes 4 quads, right? And it keeps doing this basically recursively. So the second generation will add 4 quads to each quad. So 1 becomes 4, becomes 16, 16 becomes 64, right? So the last one has 16 faces per quad. And that will give us the smoothing effect. So you can see this is like still polygonal, but this will be a lot more smoothed out. Okay, next step is to actually construct something like this parametrically. And for that, we can actually use transforms. So most of the minimal surfaces that you will be looking at, same with gyroid, they would have some sort of symmetry in them. And there will be a module, but there will be also symmetrical components. So if you can parameterize that module, you'll be able to parameterize the symmetrical components as well. But you have to understand how to transform this geometry using symmetrical functions. So first thing we can do before we start transforming, I'm just going to bake this to show you what it would look like when it's actually baked. One thing that I realized here is this construction. Let me see. It's actually similar based on the ordering of the points, but I'm getting a lot of this triangulation. It might have to do with this ordering of points. You might want to just maybe insert the centroid somewhere else, or like to the end of this list. Maybe that will change the initial configuration, but eventually this is kind of correct, actually, like the way quads are built. So let's look at how do we populate this. So I'm first going to show you what it looks like when it's actually copied in space. So we would first do a copy of it on this side. So this would be basically copied 4 times in an array, but the copies actually are not identical, so they have rotations embedded in them. So for instance, this one, you can see that we need to rotate it somehow, but it's actually like 2 rotations. So I need to first reset my gumball to the world, and the rotations are basically along this plane 90 degrees, and we should do a horizontal. Let me see this side. Actually, maybe it's this side. Yeah. So something like this that creates that type of void shape. And now we have to match the inner and out for the side. So if I go here, let's actually find this one first. So this now has to be red, and I think it's somehow like this. And this one, let's find out. So this might take a while, but you can see I actually got a bit lucky, but you can see that it's not a clear mirroring operation the way this form kind of tessellates space, right? So this one is rotating in some dimension, and this one is rotating in another direction. So these 4 elements are actually the same, but they're kind of rotated versions of each other, and there is no clear mirroring. And it actually works the same way when we stack these on top of each other. So I think this should, let me see, if I copy this here, I should tessellate it, and this should be copied on this side, and this will go in the opposite corner. So they're all being copied on the opposite top corners of the geometry, basically. So if you do that, now you get to this shape. So this one and this one are identical, so they're kind of like translating diagonally, basically. And this one and this one are identical. But once you get this sort of construction, this is kind of like an expanded gyroid, then the rest is basically like a grid. So if I do an array, so x is 3, y is 3, and z is 3, and I can just draw a cube here like that, that will basically give me the full like tessellation of the gyroid space. And this should actually work the same way for our subdivision. So if you just make a copy here, make another mesh, and put these in, let's hope the vectors, the vertices are actually touching each other, because they need to join. If you have, let's say, discontinuity, this may not work. And I'm going to bake it. And what you can see, this is now like a subdivided construction, right? So we start with the polygonal mesh, but then we recursively segment it to achieve this sort of subdivided, smoothed out version of the gyroid construction. And what's nice about this one is you can actually look at the interior with the clipping plane. Let's see, and you can see that it's tessellating the space, subdividing it into this positive and negative sides, but it's also always like following this type of minimal surface construction. So the geometry, the topology is quite nice actually, but it's built out of the symmetry of the module. Okay, so I want to show you one last thing. So just like the way I did this manually, you can actually do it using the transform. So let's actually quickly look into that. So I'm going to disable this for now. So go back here to my mesh construction. So I'm going to pull it here. So the initial box actually has a dimension, and I think it was 2. So let's look into that. So it's x is 1, y is 1, z is 1. So let's try to move this first in this direction. So I'm going to move it to where's our construction plane? So we can do it along y direction, and I'm going to do it by unit of 2. But then you can see this needs to be rotated, right? So we need to first rotate it and then translate it. So what is that rotation? So if I do rotate an object in a plane, and we can either do -90 to 90, and we need to define a plane. So it could be a horizontal rotation or a vertical rotation. We need to figure that out. So this is the mesh. Let's do -90, and we need this to be degrees. So if I rotate it this way, let's see, let's hide this one. Let's hide these as well. And I'm going to hide this too. So I have the base construction here, and that's something we need to match, right? So I need to match it along this edge. So what is my rotation such that it will actually match this edge? So what if it's in the plus direction? This may actually not work either. So maybe we need a secondary rotation, right? So let's go back to here and try to figure this out. So we have this. Now if I copy it by 2 units, what is the rotation here? So if I rotate it this way and then this way, maybe? Well, that's actually not correct. Let's go this side and this side. Oh, that doesn't work either. So let's find out. So this one is facing in. So it seems like it could be this side here. Maybe we need to mirror it actually. Well, let's say we do rotate it this way, and then, well, then we cannot do here. No, this is also creating an aperture. What if we did rotate it this way? and then rotate it this way. No. The rotations are a bit tricky. Let me find it out. So this way and this way. Okay, so that kind of works, right? So we need to kind of study it a bit. So I did the YZ negative 90 and then XY plus 90. I guess that's kind of what it is. So this is like XY plus 90, and then we did another YZ. So if I do YZ plane, and that seems correct. And then if I move this, that is exactly the shape that I had, right? So what's nice here is that we have 3 transformations. So normally you use the geometry and then you process the transformation, but now you can actually merge these and then apply them onto a geometry. So for instance, you can do merge here, get the transformations in, and then join transformations. Where's transform? Let's go to transform, utilities, and compound transform. If you do compound transform, this will be one transform operation. And then if you did transform here, this is my base geometry, and this will be the final transformation, right? So this will be very handy when you want to do, let's say, multiple transformations that are same, or they might be in an array. So you can actually use this type of construction. And I think that's kind of what I did as well here. Let me see. So I have 3 transformations and I'm joining them. And like these are basically serially constructed, if I'm not mistaken. So I'm doing rotations here as well. Okay, so they are basically individual constructions. So let's see. Let's find out where this is. Let me just hide this. Yeah, it's somewhere here, I think. It's kind of overlapping with what is already constructed. Yeah, so I was able to build this module, but then I'm actually making an array of it, right? So this is kind of an array. So we can also do it that way. So let's go back here. So we did 1. So this is one of the transform geometries. The original mesh is here, so let's bring it back. So these 2, actually, this is actually incorrect. It's good that I noticed it because you can see that this is kind of creating this pocket. So it's actually not correct. So let's try to find out. But now that we have this built, maybe we can actually rotate this to see how it would work. So I'm just going to hide these because they're doing it in place. So if I do 90 this way, and then, yeah, I think this is correct, right? So negative 90, negative 90. So this should be it. All right. So I'm going to keep this as is. And the cool thing is, like, if you did weld and join here, and then you did Catmull-Clark, they should actually form one continuous surface now. So if I bake this, this would be one continuous surface like that, right? So that's exactly kind of like a step towards this, basically. Okay, so we did this one. Let's look at the one on the other side. So I'm going to do, let's see, I'm going to make a copy of it. And let's figure out what the rotation is here. So if I do this side this way, and then maybe this direction, that's actually not correct. Like, we need to attach it to this side, actually. So let's go back. We need to find probably some alignment with this edge here. So if I rotated it 180, I think that kind of gives me the shape I want. So if I do a copy of the rotation and then did 180. And then we need to transform it. We need to move it to in the positive direction in this way, in the positive x direction. That's kind of the shape that I want, right? So I can just make another merge of these transforms. And this needs to be x, not g. G is geometry, x is the transform. So that will make a compound transform. And if I apply it to the base geometry as a transform operation, I'll get this shape basically. So let's add this to our construction and see if it's building it the way we want. So now we have a third piece added. I'm seeing this kind of edge. It might have to do with maybe this vertex being not fully fused, but it seems to work fine. One way to check that as well is before you weld it, you might want to just bake these and make sure that you have the back faces flowing in the right direction. So right now it looks like this is actually correct, right? So this is kind of looking fine. Like the red faces are facing the same direction, the white faces are continuous as well, and that's exactly what we want. Okay, so what is the transformation for the final? So if I move this around, maybe it's also 180. Let's try that. If I do 180, that's actually correct, right? So this one, I can start with this shape here, and we have its transformation. What would be nice is, I'm wondering if we can use the original shape, but if not, we can also transform this guy. So it's going to be actually this transform applied to this, right? So I can just use this transform here, but it's actually moving it in a positive direction. We probably need to change it again. Okay, anyway, so maybe we want to use this transform shape, but just move it, I guess, right? So we just want to move it in this direction, and then we want to rotate it 180 in place. Oh, but it requires a rotation plane, right? So that's not what we can do. So that's kind of the issue. Like you want to rotate it using the center geometry, and if you don't, it won't rotate it correctly. It will rotate it around this origin. So we need to actually do another transformation on the base geometry and then translate it here, which is going to be a bit tricky, but I guess we can do it. So let's find this out. So if we do, what if we just take this one, since we are doing, where is it? It's actually here. We need this to be rotated 180, right? So we already have minus 90 rotation. So if I add 180 to that, that would be plus 90. So I can start with something like this here. So what if I do plus 90? And I just move this 2 units in this way, and then maybe 2 units in this way too. So it could actually be XYZ vector with 2 and 2. I guess this should work. So if I do transformation here, is that correct? Let's see, this one is incorrect. This rotation though, oh, because is it the wrong plane? Well, we need to rotate this way, and then, okay. Let's do another rotation here just to be safe. So I'll just do 180. There are a bunch of ways we can do this, but okay, that kind of connects well, I guess, but I'm not actually seeing the right type of connection. Is it? Let's see. So we need to connect to here. This is actually rotating. Oh, and the what XY. Okay, that's why. We need this to be 180. All right, that is correct now. So I had to change the plane. Basically, we need the plane to be XY rotation. And that seems to be correct. All right, so now we have this as a transformation, and I'm going to add it here. Perfect. So now if I join it here, this is the module basically, right? So if I bake it, this is my gyroid construction. So let's check it. Oh, this is actually incorrect. This is what I was mentioning with the direction. You can see the back face is actually not merging this correctly. So it's good that we actually see this. And I also think this is not correct, not right type of merging of these surfaces. So let's find out if I'm missing anything here. So I'm going to go back, like we're trying to achieve this surface here. So maybe I'm just missing something. So we just need this. Okay, one of these needs to be changed probably. So if I do 90, it's all kinds of transformations. Let's see. Wow. Okay, I'm just going to start from scratch. Let's try to do this. I'm actually going to keep this. All right, that's good. Did it fix it? Let's see. I just deleted one component and it seems to maybe fix it. Yeah, it actually fixed it. So, all right, that's it, I guess. But I get these like seams for some reason. Maybe it's kind of the tolerance. That shouldn't actually happen. This should be kind of seamless. Maybe it has to do with this transformation data. But let's see. I have actually twos. I don't think there's any problem with the way this is scripted. Maybe we have to just flatten this out. And I think this should be fine. But we get this kind of discontinuous line here that I didn't have before, right? So you kind of see there's kind of a seam, which is kind of, it could be troublesome. Like you don't want something like that, especially next operation, we're going to actually try doing some kangaroo relaxation. But this could be like a module that we operate on, right? So one more thing we can try is to make these vertical copies that I mentioned. So rather than moving the rotated pieces, we can move them into their opposite sides. That's something to build the larger volume if we want to, or you can actually make arrays as well. So I'll let you do the volume. So the figuring out the translation for the vertical placements. So this corner will go on top of this side. This will go on top of the opposite corner, right? So that there are kind of these like diagonal translations, and you can add those as like new transforms. But one thing you can do before you kind of do the joining here, you can actually do an array. So let me show you. You can actually do a series, and with, let's say, 3 by 3 grid. So this would be my, we can do a cross-reference for A and B, and this would be my vector XYZ, I guess. So if I do it this way, would this work? Let's see. Transform. So this is my vector translation. There we go. So it's basically, I'm making a arrayed copy of all the mesh construction, and then you can do a Weaver-Ripert join for the final group, and then a subdivision. So once you do that, you would actually get this sort of continuous construction of the gyroid surface. I still see this kind of seam here. Maybe it's kind of a tolerance thing because I'm doing it on the origin. But otherwise, this is like one way of parametrically constructing these minimal surfaces. And this is just mesh construction and subdivision, right? So we can add form finding, physical simulation like kangaroo, relaxation, and other types of mesh operations on top of this as well. So give it a shot and let me know if you have any questions in the comments below. But it will be very nice to take on other types of minimal surfaces for these sorts of parametric constructions. Gyroid seems to be kind of easy because of the size of the module, but there are other versions, other minimal surfaces that are worth exploring. So give it a shot and let me know how it goes. Otherwise, I'll see you in the next video. Take care.